What if everything you've ever been taught about the speed of light is a lie? Recent discoveries in quantum physics and cosmology are revealing that light might be capable of moving infinitely fast under certain conditions, and the universal speed limit we've believed in for over a century could be an elaborate illusion created by the very fabric of space and time itself. The story starts with something that happened in laboratories around the world in the early 2000s. Scientists began achieving something that Einstein's relativity said was impossible. They made light travel faster than the speed of light, not by a little bit, but by factors of hundreds, thousands, even millions. In some experiments, light pulses appeared to exit materials before they had even finished entering them. This wasn't science fiction. It was happening in real labs with real equipment, documented in peer-reviewed journals. Dr. Lijun Wang at NEC Research Institute achieved something that should have been impossible. He sent a light pulse through a specially prepared cesium gas and watched it emerge from the far side before it had finished entering the near side. The peak of the pulse traveled at 310 times the speed of light. This wasn't a measurement error or a trick of perception. It was a fundamental challenge to our understanding of causality itself. The implications were staggering. If information could travel faster than light, it could theoretically arrive before it was sent. This would shatter the foundation of Einstein's relativity, which depends on the speed of light being an absolute cosmic speed limit. Yet here was light itself breaking that limit, recorded by instruments and verified by multiple independent teams. Similar experiments followed around the globe. At Harvard University, researchers slowed light down to walking speed, then later made it travel backward in time. At the University of Rochester, scientists created light pulses that moved at negative velocities. Each experiment added another crack to our certainty about light's behavior. The universal constant that had seemed as solid as mathematics itself was revealing hidden flexibility. The key to understanding these phenomena lies in something called group velocity versus phase velocity. When we normally talk about the speed of light, we're referring to phase velocity, how fast the wave crests move. But information and energy travel at group velocity, how fast the overall pulse moves. In normal materials, these speeds are the same, but in specially engineered materials with exotic properties, they can be dramatically different. Metamaterials, artificially structured materials with properties not found in nature, have pushed these effects to extremes. Scientists have created materials with negative refractive indices where light bends backward. Others have built materials where the group velocity of light becomes negative, meaning pulses travel in the opposite direction to their phase velocity. These aren't just laboratory curiosities. They're revealing fundamental truths about the nature of light and space. But the real revelation comes when we zoom out to cosmic scales. The speed of light in vacuum, 299,792,458 meters per second, might not be a fundamental limit at all. It might simply be the speed at which space itself can process information. Think of it like the refresh rate of a cosmic computer screen. The universe might be capable of much faster processing, but our local region operates at this particular frame rate. Recent observations from the James Webb Space Telescope have found galaxies that appear too mature for their age, existing just a few 100 million years after the Big Bang, but showing signs of billions of years of evolution. While astronomers debate various explanations, one possibility is that the early universe operated under different physical constants, including a different effective speed of light. The cosmic speed limit might not be constant across time and space. Quantum entanglement provides another clue that our understanding of cosmic speed limits is incomplete. When two particles become entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance and spent years trying to prove it wrong. He failed. Quantum entanglement is real, verified in countless experiments, and it appears to operate instantaneously across any distance. The standard explanation is that no information actually travels between entangled particles. The correlation is instantaneous, but you can't use it to send messages faster than light. But recent experiments have pushed the boundaries of this interpretation. Quantum teleportation, quantum cryptography, and quantum computing all rely on effects that seem to transcend the light-speed barrier in subtle but measurable ways. The cosmic microwave background radiation, that ancient light from when the universe first became transparent, carries information that challenges our assumptions about light speed. This radiation has been traveling for 13.8 billion years, yet it shows patterns that suggest instantaneous correlations across regions that should never have been in causal contact. The horizon problem in cosmology, why distant parts of the universe have the same temperature when they've never had time to exchange information at light speed, hints that information might have traveled faster than light in the early universe. Cosmic inflation theory attempts to solve this by proposing that space itself expanded faster than light in the universe's first fraction of a second. But this raises a profound question. If space can expand faster than light, what does that tell us about the nature of the speed limit itself? Perhaps the speed of light isn't a limit on how fast things can move through space, but rather a limit on how fast space can process the movement of things through it. The recent discovery of fast radio bursts has added another piece to this puzzle. These mysterious signals, lasting just milliseconds but releasing more energy than our sun produces in days, show dispersion patterns that don't quite match our models of how light should behave traveling through intergalactic space. Some bursts appear to arrive slightly earlier than they should, as if they've taken shortcuts through space-time that our current physics doesn't account for. Speaking of cosmic mysteries that challenge our understanding, if you're fascinated by how space travel might be fundamentally limited by physics we don't fully understand, you should check out my video, Why Anyone Who Goes to Mars Will Never Come Back to Earth. It explores how the same physical constants that might limit light speed also create insurmountable barriers for human space exploration. The universe seems designed to keep us isolated in ways we're only beginning to comprehend. Quantum field theory reveals that empty space isn't actually empty, but seethes with virtual particles constantly popping into and out of existence. These quantum fluctuations create what physicists call the quantum vacuum, and this vacuum has properties that affect how light travels. In regions where the quantum vacuum has different properties, perhaps near black holes or in the early universe, light might behave very differently than it does in our local cosmic neighborhood. The Casimir effect demonstrates that quantum vacuum fluctuations have real, measurable effects. Two metal plates placed extremely close together in vacuum experience a force pushing them together because certain quantum fluctuations are excluded from the space between them. This shows that the properties of empty space can be modified, and if space's properties can change, so might the speed of light within that space. But before we dive even deeper into these reality-breaking discoveries, make sure to subscribe to the channel and give a thumbs up. The journey we're about to take together challenges some of the most fundamental assumptions about our universe, and your support helps me bring you more mind-expanding content that connects you to the cutting edge of cosmic discovery. Recent experiments with Bose-Einstein condensates have created conditions where light behaves in ways that seem to violate our understanding of speed limits. In these ultra-cold quantum states, scientists have stopped light completely, stored its information in atomic states, then released it again later. They've also created conditions where light appears to travel backward in time, emerging from a medium before it entered. These aren't just laboratory tricks, they're revealing fundamental properties of how information and energy propagate through different states of matter. The The holographic principle, emerging from black hole physics, suggests that all the information in a volume of space might be encoded on its boundary. If our three-dimensional reality is actually a projection from a two-dimensional surface, then the speed of light might not be a fundamental limit, but rather the rate at which this holographic projection updates. Reality itself might be running at the speed of light, like a cosmic computer simulation with a specific processing speed. String theory proposes that fundamental particles are actually tiny vibrating strings in higher dimensions. In this framework, what we perceive as the speed of light might be determined by the geometry of these extra dimensions. If the extra dimensions have different sizes or shapes in different regions of the universe, the effective speed of light could vary. We might be living in a region where the dimensional geometry creates our particular speed limit. Dark energy, the mysterious force accelerating the universe's expansion, might be connected to the nature of light speed. Some theories propose that dark energy is actually a manifestation of quantum vacuum energy, the same energy that creates virtual particles. If this energy varies across space or time, it could affect how light propagates. Regions with different dark energy densities might have different effective speeds of light. The recent detection of gravitational waves by LIGO opened a new window on the universe and revealed something interesting about cosmic speed limits. Gravitational waves travel at exactly the speed of light, confirming Einstein's prediction, but they also showed us that space-time itself can be stretched and compressed by passing waves. If space-time is flexible enough to be warped by gravitational waves, it might be flexible enough to allow faster-than-light travel under extreme conditions. Wormholes, theoretical shortcuts through space-time, would allow faster-than-light travel without actually exceeding the local speed of light. You wouldn't be moving faster than light through space, you'd be taking a shortcut through folded space-time. While we have no evidence that wormholes exist, the mathematics of general relativity allows for them. If they do exist, they would make the speed of light irrelevant for long-distance travel. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a theoretical method of faster-than-light travel that doesn't violate relativity. Instead of moving faster than light through space, the drive would contract space in front of a spacecraft and expand it behind, creating a warp bubble that could travel faster than light while the ship inside remained stationary relative to local space. Recent research has shown this concept might be more feasible than originally thought. Quantum tunneling allows particles to pass through barriers that should be impossible to cross according to classical physics. Photons can tunnel through barriers faster than they could travel the same distance in free space, effectively exceeding the speed of light for short distances. While this doesn't allow faster-than-light communication over large distances, it shows that the speed of light barrier can be circumvented under certain quantum conditions. The delayed choice quantum eraser experiment reveals something even stranger about the nature of light and information. In this experiment, decisions made about how to measure photons can retroactively determine how those photons behaved in the past, even after they've already been detected. This suggests that information about quantum states might propagate backward in time, challenging our understanding of causality and the role of light speed in limiting information transfer. The phenomenon of superluminal motion observed in astronomical jets provides compelling evidence that the speed of light barrier can be circumvented in nature. Quasars and active galactic nuclei shoot jets of plasma at velocities that appear to exceed the speed of light when viewed from Earth. While this is partly explained by relativistic effects and viewing angles, some observations suggest genuine faster-than-light motion. These cosmic particle accelerators might be revealing natural mechanisms for exceeding light speed that we don't yet understand. Cherenkov radiation occurs when charged particles travel through a medium faster than light travels in that same medium. While this doesn't violate the universal speed limit in vacuum, It demonstrates that light speed can be context-dependent. In water, light travels at only 75% of its vacuum speed, allowing particles to exceed this reduced limit and create the characteristic blue glow of Cherenkov radiation. This shows that what we call the speed of light is actually variable depending on the medium. Recent discoveries about the quantum vacuum suggest it might not be the empty space we once thought. Quantum field theory predicts that vacuum should have enormous energy density, so much that it should curve space-time dramatically. The fact that we don't observe this suggests either our understanding of quantum fields is wrong, or that something is cancelling out most of the vacuum energy. If vacuum energy can be manipulated, it might be possible to create regions where light travels at different speeds. The cosmic web, that vast network of dark matter filaments connecting galaxies, might affect light propagation in ways we haven't considered. Dark matter doesn't interact electromagnetically, but it does curve space-time through gravity. Light traveling along dark matter filaments might experience subtle changes in effective speed due to gravitational effects. Over cosmic distances, these small changes could accumulate into measurable deviations from the expected light travel time. Metamaterials research has achieved what once seemed impossible: materials with negative refractive indices that bend light backward. Scientists have created cloaking devices that guide light around objects, making them invisible. They've built materials that slow light to walking speeds or speed it up beyond its vacuum velocity. These achievements suggest that the speed of light is far more malleable than we previously believed, limited only by our ability to engineer the right conditions. The double-slit experiment, quantum mechanics' most famous demonstration, reveals something profound about the nature of light and information. When we observe which slit a photon passes through, it behaves like a particle. When we don't observe, it behaves like a wave passing through both slits simultaneously. But here's the kicker: the decision to observe can be made after the photon has already passed through the slits, yet it still affects the photon's behavior retroactively. This suggests information about measurement choices propagates backward in time. Quantum entanglement swapping allows scientists to entangle particles that have never interacted directly. By entangling particle A with particle B and particle B with particle C, particles A and C become entangled even though they've never been in contact. This process can be extended to create networks of entangled particles spanning vast distances. If entanglement truly operates instantaneously, these quantum networks might provide a foundation for faster-than-light information transfer. The EPR paradox, proposed by Einstein, Podolsky, and Rosen in 1935, was meant to show that quantum mechanics must be incomplete because it seemed to require faster-than-light influences. Bell's theorem later proved that any theory reproducing quantum mechanical predictions must include non-local effects. Experiments consistently violate Bell's inequalities, confirming that nature is fundamentally non-local. The universe operates through instantaneous connections that transcend the light-speed barrier. Recent experiments with quantum teleportation have achieved record-breaking distances. Chinese scientists have teleported quantum states between ground stations and satellites, demonstrating quantum communication over thousands of kilometers. While this doesn't teleport matter or energy faster than light, it does transfer quantum information instantaneously. As our understanding of quantum information improves, we might discover ways to leverage these effects for practical, faster-than-light communication. The measurement problem in quantum mechanics, why observation causes wave function collapse, might be connected to the nature of light speed limits. Some interpretations suggest that consciousness or information processing plays a fundamental role in quantum mechanics. If consciousness operates through quantum processes that transcend classical space-time limitations, It might provide a mechanism for faster-than-light information transfer that doesn't violate physical laws. Pilot wave theory, an alternative interpretation of quantum mechanics, proposes that particles have definite positions and velocities guided by a quantum field. In this theory, the quantum field provides instantaneous guidance to particles regardless of distance. While this doesn't allow faster-than-light signaling, it suggests that nature uses faster-than-light mechanisms to maintain quantum correlations. The speed of light might be a limit on classical information transfer, but not on quantum guidance. The many-worlds interpretation of quantum mechanics suggests that every quantum measurement splits reality into multiple parallel universes. If these parallel worlds can influence each other through quantum interference, information might flow between them faster than light travels within any single world. The speed of light might be a barrier within each universe, but not between universes. Reality itself might operate at speeds that transcend our local light speed limit. Retrocausality in quantum mechanics allows future events to influence past states. Experiments with delayed choice and quantum erasers demonstrate that decisions made in the future can determine how particles behaved in the past. This suggests that information can flow backward in time, making the speed of light irrelevant for certain types of information transfer. The universe might be a block universe where all times exist simultaneously, connected by influences that operate outside our normal understanding of causality. The holographic principle suggests that our three-dimensional reality might be encoded on a two-dimensional boundary. If true, the speed of light might not be a fundamental limit, but rather the rate at which information flows from this boundary into our perceived reality. The real universe might operate at much higher speeds, with our light speed limit being an artifact of how we perceive the holographic projection. We might be living in a cosmic simulation running at light speed. The discovery of tachyons, hypothetical particles that always travel faster than light, remains one of physics' most tantalizing possibilities. While no tachyon has ever been detected, the mathematics of relativity doesn't forbid their existence. Tachyons would have imaginary mass and would travel backward in time from our perspective. Some theories suggest that tachyons might exist in parallel dimensions or in regions of space-time with different physical properties. If tachyons are real, they would prove that faster-than-light travel is not only possible, but might be commonplace in parts of the universe we can't observe. The cosmic inflation period, when the universe expanded faster than light in its first fraction of a second, demonstrates that space itself can exceed the speed of light. During inflation, regions of space that are now separated by billions of light-years were once in causal contact. This suggests that the speed of light is not a fundamental barrier to the expansion of space itself. If space can expand faster than light, perhaps it can also contract faster than light, creating natural wormholes or shortcuts through the cosmos. Recent observations of gamma-ray bursts, the most energetic explosions in the universe, have revealed something puzzling about light propagation over cosmic distances. High-energy photons from these bursts sometimes arrive at Earth slightly earlier than lower-energy photons from the same event. This could indicate that the speed of light varies with photon energy, or that space-time has a granular structure that affects different wavelengths differently. Either possibility would fundamentally change our understanding of light's behavior. The quantum Zeno effect demonstrates that frequent observation can freeze quantum evolution, preventing particles from changing states. Conversely, the anti-Zeno effect shows that certain types of observation can accelerate quantum processes. These effects suggest that the rate of physical processes, including light propagation, might be influenced by observation itself. In regions of the universe with different observation densities or types of conscious observers, light might travel at different effective speeds. Dark photons, hypothetical particles that interact only weakly with ordinary matter, might provide a mechanism for faster-than-light information transfer. These particles would be like regular photons but would travel through extra dimensions or parallel spaces where different speed limits apply. While dark photons remain theoretical, experiments are actively searching for them. If discovered, they might reveal a hidden sector of physics where our speed of light limitations don't apply. The AD-CFT correspondence, a profound connection between gravity theories and quantum field theories, suggests that our universe might be holographically encoded on its boundary. In this framework, what we perceive as the speed of light might be an emergent property of how information flows from the boundary into the bulk space. The fundamental speed of information transfer might be much higher, with our observed light speed being a derived quantity that emerges from deeper physics. Quantum error correction, essential for quantum computing, relies on the ability to detect and correct quantum errors faster than they can accumulate. This requires information processing that operates on timescales shorter than decoherence times. In some quantum systems, this effective information processing appears to operate faster than light could travel between the relevant components. While this doesn't violate relativity, it suggests that quantum information can be processed in ways that transcend classical speed limitations. The black hole information paradox reveals deep connections between gravity, quantum mechanics, and information theory. If information falling into a black hole is preserved on its event horizon, as the holographic principle suggests, then information might be processed at the horizon faster than light could travel across the black hole's interior. This would require information transfer mechanisms that operate outside our normal understanding of space-time limitations. Warp drive research has made surprising progress in recent years. NASA's EagleWorks laboratory has investigated whether the Alcubierre drive concept might be feasible with realistic energy requirements. While still highly speculative, some researchers have proposed modifications that could reduce the exotic matter requirements from impossible to merely extremely difficult. If warp drives are possible, they would make the speed of light irrelevant for space travel, allowing faster-than-light journeys without violating local physics. The emergence of time from quantum entanglement, as proposed in recent theories, suggests that time itself might not be fundamental, but rather an emergent property of quantum correlations. If time emerges from entanglement, and if entanglement operates instantaneously, then the fundamental level of reality might operate outside of time altogether. The speed of light might be a property of emergent space-time, rather than a fundamental limit on information transfer. Quantum tunneling time measurements have revealed something strange about how long it takes particles to tunnel through barriers. Some experiments suggest that tunneling happens instantaneously, regardless of barrier thickness. This would mean that quantum information can traverse any distance in zero time under the right conditions. While this doesn't allow faster-than-light communication in the classical sense, it suggests that quantum processes might operate outside normal space-time limitations. The cosmic neutrino background, relic particles from the early universe, might carry information about faster-than-light processes from the universe's first moments. These neutrinos decoupled from matter when the universe was just 1 second old, potentially preserving information about physical processes that operated under different rules than today's physics. As we develop better neutrino detection methods, we might discover evidence of faster-than-light phenomena from the universe's youth. Magnetic monopoles, if they exist, would create electromagnetic fields that extend infinitely in all directions. The interaction between magnetic monopoles would be instantaneous, regardless of distance, similar to how gravitational effects propagate at light speed, but gravitational potential extends infinitely. If magnetic monopoles exist, they might provide a mechanism for faster-than-light information transfer through their electromagnetic interactions. The vacuum birefringence effect recently observed near neutron stars shows that strong magnetic fields can change the properties of empty space itself. In extreme magnetic fields, vacuum becomes birefringent, splitting light into different polarizations that travel at slightly different speeds. This demonstrates that the speed of light in vacuum is not truly constant, but depends on the electromagnetic environment. In regions with exotic field configurations, light might travel at dramatically different speeds. The phenomenon of negative group velocity in specially designed optical materials has shattered our intuitive understanding of how light propagates. In these metamaterials, light pulses can travel backward, emerging from the entrance before they've finished entering. While this doesn't violate causality for information transfer, it demonstrates that our concept of light speed is far more complex than a simple universal constant. The peak of a light pulse can travel at any speed, including negative speeds, while still preserving the fundamental structure of space-time. Quantum field theory predicts that virtual particles constantly pop into existence and annihilate in the quantum vacuum. These virtual particles can travel faster than light because they exist for such brief periods that the uncertainty principle allows them to violate energy conservation temporarily. While virtual particles can't carry information faster than light, their existence proves that faster-than-light motion is not only possible, but happening constantly throughout the universe at the quantum level. The cosmic web's large-scale structure shows correlations that extend across billions of light-years, far larger than the distance light could have traveled since the Big Bang. These correlations suggest that information about the universe's initial conditions propagated faster than light during the inflationary epoch. If inflation can create faster-than-light correlations, similar mechanisms might still operate in extreme environments like black hole horizons or during cosmic phase transitions. Recent experiments with squeezed light have achieved information transfer rates that approach theoretical limits. By manipulating the quantum properties of light, scientists can encode information in ways that seem to exceed classical bandwidth limitations. While this doesn't enable faster-than-light communication, it suggests that light carries far more information than we previously realized. The speed of light might limit the propagation of energy and matter, but quantum information might follow different rules. The discovery of axions, hypothetical particles that could make up dark matter, might revolutionize our understanding of cosmic speed limits. Axions would interact so weakly with ordinary matter that they could travel through the universe virtually unimpeded. If axions exist and can be manipulated, they might provide a medium for faster-than-light communication that bypasses the electromagnetic limitations that constrain photons. The dark sector of physics might operate under entirely different speed limits. Topological quantum states, which protect quantum information from environmental interference, might enable information processing that transcends classical space-time limitations. These states can maintain quantum coherence over macroscopic distances and times, potentially allowing quantum information to propagate in ways that don't respect classical speed limits. As we develop topological quantum computers, we might discover that quantum information can be processed faster than light could travel between the processing elements. The holographic principle's implications for the speed of light become even more profound when we consider black hole complementarity. This principle suggests that information falling into a black hole exists simultaneously inside the black hole and encoded on its surface. For this to work, information must somehow be processed faster than light could travel from the surface to the interior. The resolution might require abandoning our classical notions of space-time and embracing a reality where information processing transcends speed of light limitations. Quantum chromodynamics, the theory describing the strong nuclear force, reveals that quarks are confined within protons and neutrons by forces that operate instantaneously. The strong force doesn't diminish with distance like electromagnetic or gravitational forces. It remains constant or even increases with separation. This suggests that nature already employs faster-than-light mechanisms to maintain the structure of atomic nuclei. The speed of light might govern electromagnetic phenomena, but not the strong force. The measurement of quantum entanglement between particles separated by cosmic distances has confirmed that quantum correlations operate instantaneously across any distance. Experiments using photons from distant quasars have ruled out local hidden variable theories, proving that quantum mechanics requires genuine faster-than-light correlations. While these correlations can't be used for communication, they demonstrate that the universe is fundamentally non-local at the quantum level. Cosmic strings, if they exist, would be one-dimensional defects in space-time left over from the early universe. These hypothetical objects would have extraordinary properties, including the ability to move at nearly the speed of light and create closed time-like curves when they intersect. If cosmic strings exist and can be manipulated, they might provide a mechanism for faster-than-light travel or communication through their effects on space-time geometry. The recent discovery of time crystals, materials that repeat in time rather than space, challenges our understanding of temporal symmetry. These exotic states of matter maintain periodic motion without energy input, seemingly violating the second law of thermodynamics. If time crystals can be engineered to operate at quantum scales, they might provide a mechanism for information storage and processing that operates outside normal temporal constraints, potentially enabling faster-than-light information transfer through temporal rather than spatial channels. Quantum error correction protocols have achieved something remarkable. They can detect and correct quantum errors faster than the errors can propagate through a quantum system. This requires information processing that operates on timescales shorter than light could travel between distant parts of the system. While this doesn't violate relativity, it suggests that quantum information can be processed in ways that effectively transcend classical speed limitations through clever encoding and parallel processing. The anthropic principle takes on new meaning when we consider the possibility that the speed of light is not fundamental. If the universe is vast enough to contain regions with different physical constants, we naturally find ourselves in a region where the speed of light allows for stable atoms, chemistry, and life. Other regions might have different speed limits that make them uninhabitable. Our observed speed of light might be an environmental condition rather than a fundamental law. Loop quantum gravity suggests that space-time itself is quantized at the smallest scales, composed of discrete loops and nodes rather than smooth geometry. In this framework, the speed of light might emerge from the rate at which information can propagate through this quantum network. At scales smaller than the Planck length, space-time might not exist in the classical sense, and different propagation rules might apply. The speed of light could be an emergent property of quantized spacetime rather than a fundamental constant. The phenomenon of superluminal tunneling has been demonstrated in multiple laboratory experiments where particles appear to traverse barriers faster than light could travel the same distance in free space. Quantum tunneling allows particles to pass through energy barriers that should be classically forbidden, and the tunneling time seems to be independent of barrier thickness. This suggests that quantum processes can operate outside the normal constraints of spacetime, with information about particle states propagating instantaneously through quantum fields. Recent advances in quantum teleportation have achieved something that sounds like science fiction: the instantaneous transfer of quantum states across arbitrary distances. While this doesn't teleport matter or energy, it does transfer the complete quantum information that defines a particle's state. Chinese scientists have demonstrated quantum teleportation between ground stations and satellites, proving that quantum information can be transferred faster than any classical signal could travel the same distance. The cosmic microwave background radiation shows patterns that shouldn't exist if the speed of light were truly fundamental. The horizon problem in cosmology arises because regions of the universe that appear to have the same temperature have never been in causal contact at light speed. The standard solution involves cosmic inflation, but this requires space itself to expand faster than light. If space can exceed light speed during inflation, perhaps it can do so under other extreme conditions as well. Dark energy, the mysterious force accelerating cosmic expansion, might be connected to the nature of light propagation. Some theories propose that dark energy emerges from quantum vacuum fluctuations, the same fluctuations that create virtual particles. If vacuum energy can be manipulated or varies across space, it might create regions where light travels at different effective speeds. The accelerating expansion of space might be creating conditions where the speed of light is no longer constant. The discovery of gravitational waves by LIGO revealed that these ripples in space-time travel at exactly the speed of light, confirming Einstein's prediction. However, the detection also showed that space-time itself can be stretched and compressed by passing waves. If space-time is flexible enough to be warped by gravitational waves, it might be possible to create artificial warping that allows faster-than-light travel without violating local physics. The Alcubierre warp drive concept relies on precisely this possibility. Quantum field theory in curved space-time predicts that the vacuum state depends on the observer's motion and the gravitational field. Near black holes or in accelerating reference frames, the vacuum appears to be filled with particles from the perspective of certain observers. This observer-dependent nature of the vacuum suggests that the speed of light might also be observer-dependent in extreme gravitational environments. What we measure as the speed of light might be specific to our particular location and motion in the universe. The delayed choice quantum eraser experiment demonstrates that decisions made in the future can retroactively determine how photons behaved in the past. This suggests that quantum information can propagate backward in time, making the speed of light irrelevant for certain types of information transfer. The experiment shows that the act of measurement can influence events that have already occurred, implying that information about measurement choices travels faster than light or outside of time altogether. Metamaterials with negative refractive indices have achieved cloaking effects that guide light around objects, making them invisible. These materials can also create superlenses that focus light beyond the diffraction limit, effectively allowing information transfer at resolutions that should be impossible. If metamaterials can manipulate light in such exotic ways, they might eventually enable the creation of materials where light travels faster than its vacuum speed, or where information can be transferred through non-electromagnetic channels. The many-worlds interpretation of quantum mechanics suggests that every quantum measurement creates parallel universes. If these parallel worlds can influence each other through quantum interference, information might flow between them at speeds that transcend the light speed limit within any single world. The speed of light might be a barrier within each universe, but not between universes. Reality itself might operate through faster-than-light connections between parallel worlds. Quantum entanglement swapping allows the creation of entangled networks where particles that have never interacted become correlated through intermediate entangled pairs. These quantum networks can span vast distances and operate instantaneously, creating a kind of quantum internet that transcends classical communication limitations. While current quantum networks can't transmit classical information faster than light, they might eventually enable new forms of communication that operate through quantum channels. The holographic principle suggests that all information in a volume of space is encoded on its boundary. If our three-dimensional reality is a projection from a two-dimensional surface, the speed of light might not be a fundamental limit, but rather the rate at which this holographic projection updates. The real universe might operate at much higher speeds, with our light speed limit being an artifact of how we perceive the holographic encoding of reality. Recent experiments with Bose-Einstein condensates have created conditions where light behaves like a superfluid, flowing without friction and exhibiting quantum properties normally associated with matter. In these exotic states, light can be stopped, stored, and released, or made to travel at speeds dramatically different from its normal velocity. These experiments suggest that light's behavior is far more malleable than we previously believed, limited only by our ability to create the right quantum conditions. The cosmic neutrino background carries information from when the universe was just 1 second old, potentially preserving evidence of faster-than-light processes from the early universe. These relic neutrinos have been traveling for nearly 14 billion years, carrying information about physical conditions that might have allowed different propagation speeds. As neutrino detection technology improves, we might discover evidence of faster-than-light phenomena encoded in this ancient radiation. Magnetic monopoles, if they exist, would create electromagnetic fields that extend infinitely without diminishing, similar to how electric charges create fields. The interaction between magnetic monopoles would be instantaneous regardless of distance, providing a potential mechanism for faster-than-light information transfer. While magnetic monopoles have never been observed, some theories predict they should exist, and their discovery would revolutionize our understanding of electromagnetic phenomena and speed limits. The vacuum birefringence effect observed near neutron stars demonstrates that strong electromagnetic fields can change the properties of empty space itself. In these extreme environments, the quantum vacuum becomes polarized, affecting how light propagates. This shows that the speed of light in vacuum is not truly constant, but depends on the electromagnetic environment. In regions with exotic field configurations, light might travel at dramatically different speeds than we observe in our local space. The phenomenon of quantum coherence in biological systems has revealed that nature might already be exploiting faster-than-light quantum effects for practical purposes. Photosynthesis in plants appears to use quantum superposition to explore multiple energy pathways simultaneously, finding the most efficient route faster than classical physics would allow. Birds navigate using quantum entanglement in specialized proteins in their eyes, suggesting that biological evolution has discovered ways to harness quantum non-locality for survival advantages. Recent discoveries about the quantum vacuum reveal that empty space is far from empty, but contains a seething sea of virtual particles and quantum fields. The Casimir effect demonstrates that these quantum fluctuations exert real forces on physical objects. If the quantum vacuum can be manipulated or engineered, it might be possible to create regions where the effective speed of light is different. Some theories propose that advanced civilizations might use vacuum engineering to create faster-than-light communication networks. The cosmic web's filamentary structure shows correlations that extend across scales larger than light could have traveled since structure formation began. These correlations suggest that dark matter, which makes up 85% of all matter, might interact through forces that operate faster than light. Dark matter particles might communicate through hidden sectors of physics where different speed limits apply, creating the large-scale structure we observe through faster-than-light coordination mechanisms. Topological insulators, materials that conduct electricity on their surfaces but not in their bulk, have revealed new ways that information can propagate through quantum systems. The surface states of these materials are protected by topology, making them immune to certain types of interference. Information traveling through topological channels might be able to exceed classical speed limits because it's protected from the environmental interactions that normally constrain propagation speeds. The discovery of anyons, exotic particles that exist only in 2 dimensions, has opened new possibilities for quantum information processing. Unlike ordinary particles, anyons can be braided around each other in ways that perform quantum computations. These braiding operations appear to happen instantaneously regardless of the physical distance between the anyons, suggesting that topological quantum information might propagate faster than light through the underlying quantum field structure. Quantum error correction has achieved something remarkable, the ability to detect and correct quantum errors faster than they can accumulate and spread through a quantum system. This requires information processing that operates on timescales shorter than light could travel between distant parts of the system. While this doesn't violate relativity directly, it suggests that quantum information can be processed in ways that effectively transcend classical speed limitations through parallel quantum channels. The measurement problem in quantum mechanics, why observation causes wave function collapse, might be connected to faster-than-light information processing in the quantum realm. Some interpretations suggest that consciousness or measurement apparatus can access quantum information instantaneously, causing immediate collapse regardless of the physical size of the quantum system. If consciousness operates through quantum processes that transcend space-time limitations, it might provide a natural mechanism for faster-than-light information access. Recent experiments with quantum dots have demonstrated that electrons can tunnel between quantum states faster than light could travel the equivalent distance. These quantum transitions appear to be instantaneous, suggesting that quantum state changes operate outside normal space-time constraints. If quantum state transitions can happen faster than light, they might provide a mechanism for information processing that transcends classical speed limits. The AD-CFT correspondence, deep connection between theories of gravity and quantum field theory, suggests that our universe might be holographically encoded on a distant boundary. In this framework, what we perceive as the speed of light might be an emergent property of how information flows from the boundary into the bulk space. The fundamental speed of information transfer might be much higher, with our observed light speed being a derived quantity that emerges from the holographic encoding process. Cosmic inflation theory requires space itself to expand faster than light during the universe's first fraction of a second. This expansion would have carried quantum fluctuations to scales larger than the observable universe, creating correlations that extend far beyond our cosmic horizon. If inflation can create faster-than-light expansion, similar mechanisms might operate in other extreme environments, such as inside black holes or during cosmic phase transitions. The recent detection of ultra-high energy cosmic rays with energies that shouldn't be possible according to our understanding of cosmic acceleration mechanisms suggests that nature might employ faster-than-light processes we haven't discovered. These particles carry energies equivalent to a baseball traveling at 60 miles per hour, concentrated in a single subatomic particle. The acceleration mechanisms required to create such energies might involve faster-than-light interactions or exotic physics beyond our current theories. Quantum teleportation networks are being developed that could eventually span continents and even reach into space. These networks use quantum entanglement to transfer quantum states instantaneously across arbitrary distances. While current quantum networks can't transmit classical information faster than light, they demonstrate that quantum information can be transferred in ways that transcend classical communication limitations. Future quantum networks might enable new forms of communication that operate through quantum channels. The discovery of time crystals, materials that exhibit periodic motion without energy input, challenges our understanding of temporal symmetry and energy conservation. These exotic states of matter maintain coherent oscillations indefinitely, seemingly violating the second law of thermodynamics. If time crystals can be engineered to operate at quantum scales, they might provide a mechanism for information storage and processing that operates outside normal temporal constraints. Dark photons, hypothetical particles that interact only weakly with ordinary matter, might provide a mechanism for faster-than-light communication through hidden sectors of physics. These particles would be like regular photons, but would travel through extra dimensions or parallel spaces where different speed limits apply. Experiments are actively searching for dark photons, and their discovery would reveal a hidden sector of physics where our speed of light limitations might not apply. The quantum Zeno effect demonstrates that frequent observation can freeze quantum evolution, while the anti-Zeno effect shows that certain types of observation can accelerate quantum processes. These effects suggest that the rate of physical processes, including potentially light propagation, might be influenced by observation itself. In regions of the universe with different observation densities or types of conscious observers, light might travel at different effective speeds due to quantum measurement effects. The phenomenon of quantum superposition allows particles to exist in multiple states simultaneously until measured, effectively processing multiple possibilities in parallel. Recent experiments have demonstrated quantum superposition in increasingly large objects, from individual atoms to molecules containing thousands of atoms. If consciousness itself operates through quantum superposition, it might be able to access information from multiple quantum states simultaneously, effectively processing information faster than classical physics would allow through parallel quantum channels. Retrocausality experiments have demonstrated that quantum systems can be influenced by future measurements, with effects propagating backward in time. The delayed choice quantum eraser shows that decisions made after photons have been detected can retroactively determine how those photons behaved earlier. This suggests that quantum information can flow backward in time, making the speed of light irrelevant for certain types of information transfer that operate through temporal rather than spatial channels. The cosmic microwave background shows anomalies that challenge our understanding of cosmic isotropy and the speed of light's role in establishing causal connections. The axis of evil, a mysterious alignment in temperature fluctuations, suggests that the early universe might have had preferred directions or faster-than-light correlations that we don't understand. These anomalies might be evidence of physics that operated differently when the universe was young and dense. Quantum field theory in curved space-time predicts that the definition of particles and vacuum states depends on the observer's reference frame. Near black holes or in accelerating reference frames, what appears as empty vacuum to one observer appears filled with particles to another. This observer-dependent nature of reality suggests that the speed of light might also be observer-dependent in extreme gravitational environments, varying based on one's motion and position in curved space-time. The holographic principle's implications become even more profound when we consider quantum error correction in holographic systems. Recent research suggests that the holographic encoding of information includes built-in error correction mechanisms that operate faster than light could travel across the encoded region. This quantum error correction might be fundamental to how reality maintains coherence, operating through faster-than-light quantum channels that preserve information integrity. Metamaterials research has achieved negative group velocities where light pulses travel backward through materials, emerging before they finish entering. While this doesn't violate causality for information transfer, it demonstrates that our intuitive understanding of light propagation is fundamentally flawed. These materials can also create regions of stopped light or infinitely fast light propagation, showing that the speed of light is far more malleable than we previously believed. The many worlds interpretation of quantum mechanics suggests that quantum measurements don't collapse wave functions, but rather split reality into parallel branches. If these parallel worlds can influence each other through quantum interference, information might flow between them at speeds that transcend the light speed limit within any single world. The speed of light might govern communication within each branch of reality, but not between branches. Recent discoveries about quantum entanglement in condensed matter systems have revealed that entangled states can persist over macroscopic distances and times, even at room temperature. These robust quantum correlations suggest that nature has found ways to maintain faster-than-light quantum connections despite environmental interference. If biological systems can harness these effects, consciousness itself might operate through faster-than-light quantum networks in the brain. The cosmic neutrino background containing relic particles from when the universe was just 1 second old might carry information about faster-than-light processes from the early universe. These ancient neutrinos have been traveling for nearly 14 billion years, potentially preserving evidence of physical conditions that allowed different propagation speeds. Advanced neutrino detection might reveal signatures of faster-than-light phenomena encoded in this primordial radiation. Wormhole physics suggests that shortcuts through space-time might allow faster-than-light travel without violating local physics. While traversable wormholes would require exotic matter with negative energy density, recent research has explored whether quantum effects might naturally create microscopic wormholes in the quantum foam. If quantum wormholes exist, they might provide channels for faster-than-light information transfer at the smallest scales. The discovery of quantum spin liquids, exotic states of matter where quantum spins remain fluid even at absolute zero temperature, has revealed new ways that quantum information can propagate through materials. In these systems, quantum correlations can spread faster than any classical signal, creating networks of instantaneous quantum communication within the material. These effects might be scalable to larger systems, potentially enabling macroscopic, faster-than-light information transfer. Topological quantum computing relies on anyons, exotic particles that exist only in 2 dimensions and can be braided around each other to perform quantum computations. The braiding operations appear to happen instantaneously, regardless of the physical distance between the anyons, suggesting that topological quantum information might propagate through the underlying quantum field structure faster than light travels through ordinary space. The vacuum birefringence effect near neutron stars demonstrates that extreme electromagnetic fields can change the fundamental properties of empty space. In these environments, the quantum vacuum becomes polarized, splitting light into different polarizations that travel at slightly different speeds. This shows that the speed of light is not truly constant, but depends on the electromagnetic environment, opening possibilities for engineering regions with different light speeds. Quantum tunneling time measurements have revealed something strange about how long it takes particles to traverse barriers. Some experiments suggest that tunneling happens instantaneously, regardless of barrier thickness, implying that quantum information can traverse any distance in 0 time under the right conditions. While this doesn't allow classical faster-than-light communication, it suggests that quantum processes operate outside normal space-time limitations. The anthropic principle takes on new significance when we consider that the speed of light might not be fundamental, but rather an environmental condition in our region of the universe. If the cosmos is vast enough to contain regions with different physical constants, we naturally find ourselves where the speed of light allows stable atoms, chemistry, and life. Other regions might have different speed limits, making our observed light speed a local rather than universal constant. The emergence of space-time from quantum entanglement, as proposed in recent theories, suggests that space and time themselves might not be fundamental, but rather emergent properties of quantum correlations. If space-time emerges from entanglement, and if entanglement operates instantaneously, then the fundamental level of reality might operate outside of time and space altogether. The speed of light might be a property of emergent space-time rather than a fundamental limit on information transfer in the deeper quantum realm. Quantum chromodynamics reveals that the strong nuclear force operates through mechanisms that appear to transcend classical speed limitations. Quarks are confined within protons and neutrons by forces that don't diminish with distance, like electromagnetic or gravitational forces. The strong force maintains constant strength or even increases with separation, suggesting that nature already employs faster-than-light mechanisms to maintain the structure of atomic nuclei through quantum field interactions. The cosmic web's dark matter filaments show correlations across billions of light years that couldn't have been established through light-speed communication since the Big Bang. These correlations suggest that dark matter might interact through hidden forces that operate faster than light, coordinating the large-scale structure of the universe through mechanisms we don't understand. The visible universe might be just the tip of an iceberg of faster-than-light dark sector physics. Recent experiments with squeezed light have achieved information encoding densities that approach theoretical quantum limits. By manipulating the quantum properties of photons, scientists can pack more information into light beams than classical physics would allow. While this doesn't enable faster-than-light communication, it suggests that light carries far more information than we previously realized, and that quantum information might follow different propagation rules than classical information. The measurement of quantum entanglement between particles separated by cosmic distances has confirmed that quantum correlations operate instantaneously across any distance. Experiments using photons from distant quasars have ruled out local hidden variable theories, proving that quantum mechanics requires genuine faster-than-light correlations. These experiments show that the universe is fundamentally non-local at the quantum level, connected by instantaneous influences that transcend space-time. Cosmic strings, if they exist, would be one-dimensional defects in space-time left over from phase transitions in the early universe. These hypothetical objects could move at nearly the speed of light and create closed time-like curves when they intersect. If cosmic strings exist and can be manipulated, they might provide a mechanism for faster-than-light travel or communication through their effects on space-time geometry, creating shortcuts through the fabric of reality itself. The discovery of quantum error correction in biological systems suggests that nature has evolved mechanisms to protect quantum information from environmental decoherence. Photosynthesis appears to use quantum coherence to explore multiple energy pathways simultaneously, maintaining quantum effects in warm, noisy biological environments. If evolution has discovered ways to harness quantum non-locality for biological functions, consciousness itself might operate through faster-than-light quantum processes. Loop quantum gravity proposes that space-time itself is quantized at the smallest scales, composed of discrete loops and nodes rather than smooth geometry. In this framework, the speed of light might emerge from the rate at which information can propagate through this quantum network. At scales smaller than the Planck length, space-time might not exist in the classical sense, and different propagation rules might apply that allow faster-than-light information transfer. The holographic principle's connection to quantum error correction reveals that the encoding of information on holographic boundaries includes built-in mechanisms that operate faster than light could travel across the encoded region. This quantum error correction might be fundamental to how reality maintains coherence, suggesting that the universe operates through faster-than-light quantum channels that preserve information integrity across cosmic scales. Recent advances in quantum teleportation have achieved record-breaking distances and fidelities, demonstrating that quantum states can be transferred instantaneously across arbitrary distances. Chinese scientists have established quantum communication links between ground stations and satellites, proving that quantum information can be transferred faster than any classical signal could travel the same distance. These achievements point toward a future quantum internet that operates through instantaneous quantum channels. The delayed choice quantum eraser experiment demonstrates that quantum systems can be influenced by future measurements, with effects propagating backward in time. This suggests that quantum information can flow in both temporal directions, making the speed of light irrelevant for certain types of information transfer that operate through temporal rather than spatial channels. The universe might be a block universe where all times exist simultaneously, connected by faster-than-light quantum correlations. Dark photons and other hypothetical particles from hidden sectors of physics might provide mechanisms for faster-than-light communication that bypass electromagnetic limitations. These particles would interact only weakly with ordinary matter, but might travel through extra dimensions or parallel spaces where different speed limits apply. The discovery of hidden sector particles would reveal new realms of physics where our speed of light limitations might not apply. The quantum Zeno and anti-Zeno effects show that observation can either freeze or accelerate quantum evolution, suggesting that the rate of physical processes might be influenced by measurement itself. In regions of the universe with different observation densities or types of conscious observers, physical processes including light propagation might operate at different effective speeds due to quantum measurement effects that transcend classical space-time limitations. Topological quantum states protect quantum information from environmental interference through mathematical properties that are immune to local perturbations. Information stored in topological quantum states can maintain coherence over macroscopic distances and times, potentially allowing quantum information to propagate in ways that don't respect classical speed limits. These protected quantum channels might enable information transfer that transcends the light speed barrier. The cosmic microwave backgrounds anomalies, including the axis of evil and hemispherical asymmetry, suggest that the early universe might have had preferred directions or faster-than-light correlations that established large-scale patterns. These anomalies might be evidence of physics that operated differently when the universe was young and dense, possibly including faster-than-light processes that shaped the cosmic structure we observe today. If you enjoyed this video, I am sure you will love this other one at the left side of the screen, the harsh reality of why we can't travel at light speed. In this video, we break down the exponential energy requirements, time dilation, and the lethal radiation impacts you'd face as you approach light speed. See you there.